So good afternoon. Now we are going to discuss about minimum spanning trees, which is an important and an interesting topic in data structure. So before moving on to minimum spanning trees, let us discuss about what is a spanning tree first of all. So we all know spanning trees deals with the graph. What is a graph first of all? Graph is a collection of vertices which is connected by edges. So from a graph, we can obtain a spanning tree. Spanning tree is generally called as a um, subset of a graph. So, for example, this is the graph which has three vertices and three edges. From this, how we can obtain a spanning tree? So, for example, a spanning tree is a tree which is obtained from a graph which has the same number of vertices as the graph. This is our original graph G, which has A, B, and C, three vertices in total. The spanning tree of this graph will also contain a number of vertices, that is A, B, C. It is a condition for it. And what about the edges is that we obtain only V minus one number of edges, that is number of vertices minus one number of edges. In this case, this graph, the original graph, contains three edges, that is AC, CB, and BA. In a spanning tree, we'll be missing one of the edges so that we'll obtain a spanning tree. For example, in the first spanning tree, the edge AC is missing, so that we have only two edges, AB and BC. Recall once that I've said that the spanning tree contains n minus one number of edges, that is number of vertices minus one. So we'll have 2. 3 minus 1 is 2. So we'll have two edges in total here in spanning tree. And a, a single graph can have many number of spanning tree. Here we have 3 number of spanning tree for a single graph. So these are the conditions. As I already said, a graph contains uh, number of vertices and number of edges. If a spanning tree is, a graph is denoted as G, and when a spanning tree is denoted as T, it will have vertices, that is V complement as its vertices and E complement as its edges, where the number of edges of number of vertices of both graph and spanning tree is the same, and we'll have one missing edge, one of the edges missing. Next, a minimum spanning tree. So in a minimum spanning tree, we already saw a graph and a spanning tree. In minimum spanning tree, the graph will be a weighted graph. Weighted graph, we all know that the edges of the graphs will be weighted. It will be given values like 1, 2, 3, 4. Any kind of values will be given. So minimum spanning tree, it deals with the only weighted graphs and not non-weighted graphs. What are the applications is that find the cheapest way to wire your house. It is real life applications, and find the minimum cost to send a message on the internet. These are the real life applications. So before moving on to these, we'll discuss about minimum spanning tree. So here comes the properties, and also we'll discuss an example of a minimum spanning tree. So consider this as a minimum spanning tree which has four edges, A, B, C, D, and it has four vertices and 1, 2, 3, 4, 5 edges, which is weighted. For example, A and B, AB, the edge AB contains value 5, BC is weighted as 1, CD is weighted as 4, and DA is weighted as 5, and BD is weighted as 2. Now, as I already said, the edges in the minimum spanning tree or a spanning tree, the formula is number of vertices minus 1. That is, if, for example, there is 5 number of vertices, we'll have 4 number of edges in the spanning tree. Here in the different case, that is in a complete graph, we know complete graph is that every edge is connected with an edge, every vertices is connected with an edge. In that case, in the case of complete graph, the formula for calculating how many edges in a spanning tree is that E minus n plus 1, which is E stands for number of edges, n stands for number of vertices. So here we'll calculate with this. So what is an E, which stands for number of edges? So when we count, there are 5 edges. Then number of vertices, we count as 4. So 5 minus 4 is 1 and 1 plus 1 is 2. So how many edges can be removed is that we can remove 2 edges to obtain a minimum spanning tree, an MST. That is that's what I have written here. Number of edges can be removed from a spanning tree or from a graph to obtain MST is this formula E minus 1 plus 1. So evaluating this formula, we got 2. So that 2 edges can be removed to obtain a MST. And for a single spanning tree or a graph, there can be more than one minimum spanning tree, and also there are some other properties too, which I'll say now. Removing one edge from the spanning tree will make it disconnected. So we should never remove an extra edge from the spanning tree because it will make it disconnected. When we reach the condition that the graph is disconnected, the total we will not obtain a spanning tree and also a minimum spanning tree. Then adding one edge to the ST, that is spanning tree, will create a loop. That is also not accepted as a condition for a spanning tree. So adding a one edge to the spanning tree will make it as a loop. So it is not considered as a spanning tree. Then if each edge has distinct weight, then these will be one, then there will be only one MST. For example, consider this graph which has 5 5 2 4 1, which is not distinct because it has two times it has the weighted edge as 5. So it may have many number of spanning trees, but in this case one of the 5 is replaced by another number. The spanning tree looks distinct. Every weight is different from one another. So in that case there will be only one minimum spanning tree. There will be only one MST. So this is one of the main property. And only connected and undirected graph has at least one spanning tree, and a disconnected graph does not have any spanning tree. Then an important property is that the number of edges can be removed from a spanning tree to obtain MST in case of complete graph is E minus n plus 1. So we have removed, as per this, we have removed 2 edges from this, so that we can construct a minimum spanning tree using only 4 edges. So we have evaluated here. So what is the main thing about minimum spanning is that our aim of obtaining a minimum spanning tree is that we'll obtain the minimum. When we sum up all these weights, we have to get the minimum value, which gets as I already said, there will be many MSTs or many spanning trees, but which is the spanning tree which gets the lowest value as a sum of all the edges, that is said to be the minimum spanning tree. So let us see here. So in this first we try it out with removing AD and BC edge. So we are left out with AB, BD and DC edges, which has weight 5, 2 and 4, which gives us sum 11. Another a second example or a second method is we removed only B and D and BC. So we got weight 14. And again we removed AD and BD edges, so that we are left out with the weighted edges as 5, 1 and 4. If we sum up this, we'll get only 10. Then Then we'll get the sum as 8. Then we'll get the sum as 8. Then what is the strategy for minimum spanning tree is that removing any edge from the cycle gives back a spanning tree, and any new edge, if we add any new edge, has a lower cost than the old edge we have progressed. And for creating this minimum spanning tree, we have two types of algorithms, that is Prim's algorithm and Kruskal algorithm. Before moving to that, this minimum spanning tree, only complete graph, only for complete graph we have the formula E minus n plus 1. But in the case of a normal graph, we'll have the formula that it has the edges v minus 1. So here we have two algorithms to evaluate this minimum spanning tree. One is Prim's algorithm and Kruskal's algorithm. So what is Prim's algorithm is, we'll build that tree, that's minimum spanning tree, incrementally. So what we'll do is that we'll pick the lower cost edge connected to known spanning tree that does not create a cycle and expand to it to include it in the area. The main thing which involves in Prim's and Kruskal's algorithm is that no loop is allowed and it should not be disconnected. Then what about Kruskal's is that we'll build a forest that will finish as a tree. Pick the lowest cost edge not yet in a tree that does not create a cycle. Then we should expand the set of included edges to include it. So for example, a Prim's algorithm, consider this graph. So we can choose a random vertex. So now we have selected 1 as the starting or an initial vertex. Now what happens after choosing 1 as the vertex, we have to, many edges are connected to it. For example, edge which is weighted as 10, edge which is weighted as 1, edge weighted with 5. These 3 edges are there, among which we have to choose the edge which has minimum cost. That is, as we always we have to head to the minimum thing because we are dealing with the MST. So from the vertex 1 we have 3 edges, but still we have to choose the edge which has the minimum cost, which is 1. So the edge which connects 1 and 3 is selected first. So that is the first step. So yeah, it is, so now it is indicated by a blue color line to our convenience. So first this is selected, then as a result we have visited the node 3. From 1 we have visited the node 3. To find a path only we have selected the minimum cost, an edge with minimum cost, that is 1. Then from 3, now our destination node is 3. From 3 where we have to go? So again follow the same procedure. It has 3 edges, but still we have to choose the minimum cost edge, which is 3 to 4, which contains weight as 3. So that is selected. Then we have visited the node 4. From first step we started from 1, the vertex 1. Then we have reached node 3. Then now we have reached node 4, node number 4. So now we are in the 4th node. So being at the number 4th node, now we look at the edges. We have 2 edges connected from 4. That is 5, which is weighted as 5 and 4. Among these, which is the minimum? 4. So we'll visit the node 5 because that is the edge which contains minimum cost, that is 4. So we have visited here 4. From 4, so now we have destined in 5th node. I mean number node which is designated as 5. So from 5 there are 2 edges again, which connects to 2 and which connects to 6. So from 5, which edge has the minimum cost? Now 1, that is the edge which is connecting 5 and 2 has the minimum cost 1. So there we have to visit. So we reached the node 2. From node 2 there are again 3 edges which is weighted as 10, 8 and 6, among which the 2 to 6, that edge is the edge which has the minimum cost, that is 1. So we reached the 6. Now you look it overall, we started from 1 and reached 6th, and you just find where we have I mean we have not left even a vertex. We just visited all the vertices. This is all about the Prim's algorithm. We have to cover all the vertices, no, not all the edges but all the vertices, by the way of choosing the minimum cost edges. So the final cost. So the final the order we have reached is that 1, 3, 4, 5, 2, 6. So we write it as a set, the vertice 1, 3, 4, 5 and 6. So here again we'll write the order of edges we have visited. So order of edges from 1 to 3 we have chosen this weight, the weight of the edge, that is 1 comma 3. 1 comma 3, the weight of 1 comma 3 is 1. So we have to have 1 here. Then we have visited 3 to 4. So 3 to 4 contains 3. Have it as the next value, 1 plus 3. Then afterwards 4, which is 4. So 1 plus 3 plus 4, done. Then from 4 we have visited 5 to 2. So 5 to 2 is 1 again. So 1 plus 3 plus 4 plus 1. Again and 1, which is 2, 6. 2 comma 6. So we have to add these cost, only the cost, not any other vertices or anything. We have to just add the sum of the weight of the edges. That is 1 plus 3 plus 4 plus 1 plus 1, which gives 10. So this is a procedure, Prim's algorithm procedure, by which we can obtain the minimum spanning tree. So we'll have during programs we'll have the pseudocode for this, and we'll construct a program to obtain the MST of a graph. So then if the select the unmarked node u with minimum cost is done with a binary heap order of n plus m of log n. Then another method very similar to Prim's algorithm, we have another method which is called as Kruskall's algorithm, in which we have to select the edges in the order of increasing cost. Increasing cost in the sense ascending order. It has to it should be end. It should destined with the maximum cost. So what we have to do is accept an edge to expand tree or forest only if it does not cause a cycle. As I already said, it should never cause a loop or a cycle, and it should not be disconnected. Then implementation of this Kruskall's algorithm can be with adjacency list, priority queues, and also disjoint sets. Then we have to follow this Kruskall's algorithm procedure until we reach v minus 1 number of edges. For example, if we have 10 number of vertices, we have to repeat this procedure 9 times until the 9 times, 9 edges have been accepted. All the 9, if it forms a cycle or a loop, then we have to not consider that particular. Then okay, we'll take this example. Here we'll take this example where we have a graph, a graph which has 1, 2, 3, 4, 5 vertices and 5 edges in total. So we have our question is that it is a graph which contains 5 vertices and 5 edges. So how to follow this Kruskal algorithm is that we have to, first of all, we have 3 to 4 steps in total. The first step is that if the graph has parallel edges or loops, we have to first remove it. That is the first step. Here we do not have any parallel edges or loops, so uh, so it is not applicated here. Then the next step is that we have to write down all the pair of vertices. We have to write down a pair of vertices or an edge or edges. Uh, for our convenience, we'll write the edges. So we'll write the edges in an increasing order. Increasing order in the sense from small to the biggest value, from small to the largest value. So here find it out. What is the minimum value? So 1 is the minimum cost. So first we have to write down as 1, 2. It is the first edge. Again, sorry, it contains 2. So 1, 2 is taken as the first edge. Then what is the minimum among 5, 3, 3 and 12? 3 is the minimum. So we'll have either 3, 2 as an edge or as a second edge, or 3, 0 as a second edge, because both contains 3 as their weight. So that is our wish. We can take either of these. Then which is minimum among 7 and 12? 7. So 4, 2. The edge 4, 2 is, as we always know, that we'll represent an edge by vertex 1 comma vertex 2. In that node we consider 4, 2 as an edge, which contains 7 as the um, minimum cost among these the last two edges. Then again, the last edge we are considering is that the 0, 4, which contains 12 as their weight. So our order is 1, 2, then 2, 3 or 3, 0 next to next, then 3, 1, then 4, 2, then 4, 0. So this is our order. So what we are going to do at first is that we have to the number of vertices remains the same. So we can already draw the vertices and keep, or we can construct step by step. But the edges uh, should not be constructed in advance, because by Kruskal's algorithm we are going to create a path only. The edges matters here, so we are going to form edges. Consider these are all empty things, okay? The lighted lines as we have not yet created anything. So the darkened lines are the steps of construction. So at first, what happens is that the minimum cost weight, that is 2, which is between 1 and 2, is drawn. It is drawn. The next step, which is written as 2. Here, the next minimum cost, that is 3. 3 is connected between 3 and 2. So we'll have here 1, 2, 2, 3. This is the tree which we have obtained till now, only till now, till the second step. And again, going to the third step, we'll construct the third minimum cost, that is again the 3, which is between 3 and 0. So we draw it or construct it. Then the next minimum cost is 5, but we do not draw this 5. I mean, we do not construct this particular edge which is weighted as 5, which is between 3 and 1. Why? What is the reason is that it forms a cycle. The main condition of a spanning tree is that it should never contain a cyclic. A tree, a tree in general is in a cyclic graph, and also the spanning tree and the minimum spanning tree should not contain any cycle. So this is discarded. We should never consider this. So this is cancelled. That is the edge which is weighted as 3, between 3, 1 is cancelled, and we go to the next minimum cost, that is 7, number 7, which is the which is the edge 4, 2, which contains the minimum cost as 7. It does not create any cycle, so no issues, we can construct it. Then 12. again, this 12 is not constructed. Why? Because we should not consider. Why? Because it creates a circle or cycle or a loop. So we should also discard this 12. Out of these, the edges which is weighted as 5 and 12 is discarded. Without these only, the minimum spanning tree is created using Kruskil's algorithm. So this is the methodology of Kruskil's algorithm. So what is the time complexity is that the Prim's algorithm runs with order of n plus m into log n, and Kruskil's runs in order of m log m. So we'll have a quick recap. So our topic is minimum spanning tree. So what are spanning tree is that it is a subset of a graph G. A graph contains vertices and edges connected to it. So spanning tree is a subset of graph. From a graph we can create any number of spanning trees. They can be also a unique one and a number of spanning trees also. So what is the formula is that formula for edges is that it contains the same number of vertices but v minus one number of edges, that is number of vertices minus one edges. Then the important condition is it has the same number of vertices and a missing edge. Then it forms a tree. We have to form a tree only from a graph which does not contain a cyclic. We already know an acyclic graph can be also called as a tree. Then a minimum spanning tree always deals with the weighted graphs. So with weighted graphs, in the sense, in a graph the edges will be weighted, it will be assigned to some values. So those are called the weighted graphs. From those weighted graphs only we'll be able to obtain the minimum spanning trees. So the real life applications are to find the cheapest way to wire your house and the minimum cost to send a message. An important um, an important property is that number of edges can be removed from a graph to obtain a minimum spanning tree in a complete graph is e minus n plus 1. That is number of edges minus number of vertices plus 1 gives you the number of edges that can be removed to form a minimum spanning tree. We take it as an example. We have 4 vertices and 5 edges. So calculating with this formula, 5 minus 4 plus 1, which gives you 2 as an answer. So when 2 is an answer, what we have to consider is that 2 edges can be removed so that we'll obtain the minimum spanning tree. And another important property of minimum spanning tree is that if if all the edges, if each and every edge has a distinguished value, that is a unique value which is not even repeated, that is every weight or every cost of an edge should be unique. If that is the case, then there will be only one MST, one minimum spanning tree. If two or more edges have the same weight, then what happens is that it has more than one minimum spanning tree. So what is the procedure? What is the procedure is that here we have to remove any two edges from this graph. So first we have removed AD and BC. So we have left out with edges AB, BC and DC, which has values 5, 2 and 4. When we sum it up, we have 11 as as our answer. Then in the second graph, we removed the edge BD and BC. So we are left out with edges which are weighing 5, 5 and 4. When we sum it up, we'll get 14 as an answer. Then in the third graph, we removed AD and BD, two edges. Only two edges can be removed. Only that is a possible case. So we are doing like that. So as a result, we are left out with the edges which weighs 5, 1, and 4. When we sum it up, we got 10. Then at last we removed AB and DC. Now we get edges which weighs 5, 2, and 1, which gives the value 8. So it when we sum it up, 2, 5, and 1, 2 plus 5 plus 1, it gives 8. Now among these, it can have many spanning trees, but it will have only one MST. So here this 2 plus 5 plus 1 gives 8, which is the minimum cost. So this is called as the minimum spanning tree of the graph. These are all these four possible cases are the spanning tree, but this last one, which gives the sum of 8, is called as the minimum spanning tree, because when you sum it up, it gives the least value among the other spanning trees. So this is the basic thing of a MST. A tree can have many spanning trees, but which gives the minimum value is called as the MST. And for any spanning tree, inserting a new edge creates a cycle, which is that if any graph contains a cycle, then it is not at all a tree. So if that condition fails, we cannot obtain a spanning tree or a minimum spanning tree. Then removing an edge from the cycle gives back a spanning tree. As we said that a cycle cannot be a tree. So from that cycle, if any one of the edges is removed, then it will give the spanning tree. Then if new edge has a lower cost than old edge, we have progressed. That is, we are heading to obtain a minimum spanning tree. And we have to repeat b minus 1 times. That is, if an edge if a graph has 10 vertices, we have to try it 9 times. 9 times to obtain all the spanning trees. Among that, we'll obtain a MST also. Then we'll have two methods, two types of algorithm to obtain this MST. That is Prim's algorithm and Kruskal's algorithm. So procedure of Prim's is pick the lower cost edge connected to known spanning tree that does not create a cycle and expand it to include it in the tree. Then Kruskal's is pick lowest cost edge not yet in a tree that does not create a cycle. So Prim's, we just visit the nodes. The edges and also the vertices are already known in the Prim's, but in Kruskal's we'll construct it according to the arrangement of our edges, weight of the edges. Then a small recap of the Prim's algorithm. So we'll choose one random vertex. We take it as 1 here, and it can have many number of edges. But what is the what is the path to reach the next node is that we have to choose the minimum among the edges. So this one, as we see, has 3 edges, but what is the minimum among it is 1. That is the 1, 3. The edge which is connecting 1, 3, it contains 1 as the minimum cost, as its weight. So we choose that path. So choosing that path, what is the result? We reach the node 3. From 3, where we have to visit is that we have three other edges, but we have to choose the minimum one. So we'll choose this 3, 4 edge named 3, 4, which has minimum cost 3. From there we reached 4. Then we have to again analyze. Here another thing is that we should not repeat the same vertices, and we have at the same time we have to visit every vertices. That is a rule of Prim's algorithm, and also a minimum spanning tree. As we already said, it has the same number of edges as the graph, but not the same edge. So from 4, From 4 where we'll go, we have 3 edges, but we'll choose the minimum one. Here another important thing is we have 3 as the minimum cost, but we cannot go again to the same visited node, so we choose another choose from the other two, which is weighted as 5 and 4. Among weights 5 and 4, 4 is the minimum, so we choose 4 as the path, and we reach fifth node, node number 5. From node number 5, again we have 1, 2 and 3 edges, from which one weight 1 is selected, so 5, 2. So there is a path from 5, 2, so we go there too. So we came to an end 2. So from here we also we have 3 other edges. One cannot be we have 2 ones, that is as a weight, but we can't repeat again 2 to 5. It is already visited, so we have to visit a new node, so we choose 6 as the node, so we reach there. So that is all about the Prim's algorithm. So as we progress, or as we head towards each and every node, we have to make it as a set. What is the we have to identify, we have to initialize the vertex first, that is 1. From that we have to follow up every other vertices and also the edges uh, visited. As for example, here we 1, 3, so 1 is visited and 3 is visited. As a result, edge 1, 3 is visited. So we know edge is a combination of starting node and ending node. So we have represented it as 1, 3. And here it goes on, the same procedure is repeated until v minus 1 times, that is 1, 2, 3, 4, 5, 6. So 5 times we repeat this. So as a result, we'll get vertices as this is the order in which we have visited all the nodes. That is 1, 3, 4, 5, 2, 6. Then edges as 1, 3, then 3, 4, then 4, 5, then 5, 2, then 2, 6. So here to know the final cost, we have to add, for example, 1, 3. If 1, 3 is, it is weighted as 1. 1 plus 3, 4. 3, 4 contains 3. So we have to add the weights of this particular each and every edge, and we'll have a final sum which is here, it is summed as 10. So this is the minimum spanning tree of this this graph using Prim's algorithm. This is the procedure. The answer will be the same using Prim's algorithm or Kruskal's algorithm, but the procedure differs. Then Kruskal's algorithm select edges in order of increasing cost, accept an edge to expand tree or forest only if it does not cause a cycle. Then implementation can be with adjacency lists, priority queues and disjoint sets. Then again this also we have to try v minus 1 times until the v minus 1 edges have been accepted. All the edges have to be accepted, but we can discard. There is a case we can discard if the particular edge, the adding edge, I mean if we are going to construct that edge and that edge is going to form a cycle or a loop, we have to discard it. In that case alone we'll discard it. Then yes, we'll see the example of a algorithm. So first step is we have to discard all the if a graph is given, we have to discard all the parallel edges and also the loops. That is the first step we have to follow in Kruskal's algorithm if a graph is given. Then the next step is we have to write down all the edges, all the name of the edges in the increasing order. Increasing order in the sense from the smallest to the largest value. Then the next step is we have to construct one by one. The vertices are all the same, so we can first construct all the vertices, but the edges, but when it comes to edges, we have to construct one by one in the ascending order. That is from the smallest way to the largest one. If an adding edge causes a cycle or a loop, we should not consider it. It will be missing in the graph. So as a result, we will obtain a graph using a Kruskal algorithm. So what are the applications of this MST is that it is used in computer networks, telecommunications network, transportation networks, water supply networks, and electrical grids. So these are the real life application of the minimum spanning tree, and also the cluster analysis. Then in process control, then the topological observability in power systems. There are so many circuit design, everything. This minimum spanning tree is used. And there are also many properties in MST, which is that distinguished. Trees which has distinguished edges will have only one MST, one spanning tree, while if every other share is a similar weight, then it has many more spanning trees. So that is all about the minimum spanning tree. Thank you.